Welcome to the Explainer. Have you ever looked at the differential equation and just wished you had a magic wand to make it all go away? Well, you're in the right place. Today, we're going to demystify a really powerful piece of mathematical magic, the region of convergence for the Laplace transform. What is it really, and why is it such a secret weapon for engineers? Okay, so what's the big problem we're even trying to solve here? Why do we need this mathemagic in the first place? Well, it all starts with the fact that the real world is kind of messy. I mean, think about it. Imagine you're trying to predict exactly how a skyscraper is going to wobble in a huge windstorm, or how current is going to surge through a really complex circuit. These are real things happening in the real world, and they're all described by differential equations. And if you've ever been an engineering student, you know that solving those things directly can be an absolute nightmare. But what if? What if you could just wave that magic wand and turn that whole tangled mess of calculus into simple, high school-level algebra? It sounds like a fantasy, doesn't it? But it's not. That is the core promise of a technique that's been an engineer's best friend for over a century. The trick is all about shifting your perspective, moving the entire problem into a whole new world where the rules are just simpler.
And this is where the magic really begins. So let's meet the star of our show, the Laplace transform. Now, as you can see here, even though Laplace gets his name up on the marquee, this was not a solo act, not at all. The idea was built up over decades by some of the greatest minds in mathematics, like Euler, who laid the groundwork. But it was actually Oliver Heaviside who turned it into the practical, problem-solving powerhouse that engineers rely on today.
And when you use it, the effect can feel almost exactly like a magic trick. I mean, this Reddit user puts it perfectly. It's like math magic. You take a problem that seems totally impossible, you do a few clever steps, and it just simplifies. It's this incredibly elegant way to cut right through all the complexity. So how does this mathemagic actually work? Well, this slide breaks it down into a really simple three-step process. First, you transform the difficult calculus problem into a much friendlier algebra problem in what we call the S domain. Then, step 2, you solve it using the kind of stuff you learned in high school. And finally, you do an inverse transform to bring the solution back into the real world. It's kind of a classic bait and switch, but for math problems.
But, like any powerful spell, there are rules. You can't just apply this transform to any problem you feel like. There's a catch, a really important condition that makes sure the magic doesn't, backfire. See, at its heart, the Laplace transform is built on an integral. And for that integral to give us a real, finite answer, it has to converge. A simple way to think about it is this. You can't find the total area under a curve that just keeps getting steeper and steeper and goes on forever, right? The math just breaks. So the signal we're analyzing has to be, in a sense, well-behaved. So that's the big question, right? How do we draw the line between a well-behaved signal we can work with and one that's just going to break our transform? Well, that's where the region of convergence, or ROC, comes in. It's basically the gatekeeper for the entire Laplace world. The best way to think of the ROC is as a map. On this map, every single point represents a possible value for our transform variable S. The ROC is the safe zone on this map. It's the collection of all the S values where our integral converges and gives us a meaningful answer, instead of just exploding to infinity. And this is where it gets really cool. The ROC isn't just some abstract mathematical rule. It's a direct window into the stability of a real-world system. As this Redditor points out, it's the boundary between a system that works and one that goes totally haywire, sometimes literally. Think of a bridge starting to oscillate like crazy in the wind, or an amplifier circuit that produces this deafening, out-of-control screech. That's a system blowing up.
So what does this map of stability actually look like? Well, to visualize it, we use a tool called the S-plane.
The S-plane is basically a two-dimensional graph that lets us see complex numbers. The ROC shows up as a specific area on this graph. And what defines the borders of that area? Something called the poles of the system. Just think of poles as danger zones, specific points on the map where the system's response just goes infinite. The ROC is essentially the safe zone that's defined by avoiding those danger points.
And what's fascinating is that there are these really simple rules for drawing this map. For a causal system, which is most real-world systems, a light bulb only turns on after you flip the switch, the ROC is the whole region extending to the right of the rightmost pole. For a more theoretical anti-causal system, it's the region to the left. This simple rule gives us a powerful shortcut to understanding how the system behaves.
Okay, so we've got this map of stability. Why should an engineer actually care? Because this is where the abstract math suddenly translates into real-world, sometimes even life or death consequences.
The ROC is so much more than just a mathematical hoop you have to jump through. It's a powerful diagnostic tool. It lets us analyze a system's most fundamental properties, like its stability, without ever having to go through that messy process of transforming back to the time domain.
This quote from an engineer on Reddit says it all, really. You can just plot the poles, sketch out the ROC, and you immediately know if your design is stable. It's like having a crystal ball for your system, all without solving a single differential equation.
And here it is, the golden rule of the ROC. You look at the S-plane map. If the ROC, that safe zone, includes the vertical axis, the system is stable. If it doesn't, it's unstable. It's that simple. With this one visual check, an engineer can tell if a new airplane wing design is going to flutter apart in midair, or if a control system for a robot will be smooth and predictable. It's an incredibly powerful shortcut.
So, the next time you see some really complex piece of engineering, just remember that underneath the surface, there might be a simple map, the region of convergence, that's quietly ensuring everything stays stable. It's a really beautiful example of how abstract math can give us a powerful lens to understand and shape the world around us. Makes you wonder, what other hidden mathematical rules are out there governing our reality?